Welcome everyone. I am Rati Ludhani, pursuing PhD at Department of Mathematics, IIT Bombay. Today we are going to discuss week 6 sample questions, which is related to lecture 12 and 13. So let's start. Consider a cyclic group A with a generator G of order n. Which of the following is a necessary and sufficient condition for G raised to power I to be a generator of A? So, what is given for you? A is a cyclic group which is generated by a element G of order n. So that means I'll write whatever information we have, and order of G. Okay, smaller notation maybe O of G is equal to n. So this implies what? You have n elements in your set A, right? Okay. So what do you think answer should be? So they are asking when. So your question is precisely when A is equal to G raised to power I. So you need to figure out what is A, what is I. Okay, so that is your question, like when can you say G raised to power I generate A? And so you need to figure out what will be what I should be corresponding to n, or maybe you can say whatever you can say, you need to tell. Okay, so what do you think from the options? Like n and I must be relatively prime, I must be prime, n must be prime, or none of these? Do you have any guess?
Ma'am, I think I is equal to 1, then it is generated.
Yeah. When I is equal to 1, then for sure we have this. When I.
Option B was eliminated. I must be prime.
Yeah, exactly. Very good. So this option will be so I cannot be. Very good. Cannot be prime. Exactly. Right. And what else you can say? Okay. Okay. Let's try it out. So one more thing, if you say n must be prime, can you, like, this is not giving any information about I. It's just, this is just saying n is prime. Okay. So and one more thing, they said necessary and sufficient condition. So it should be if and only if. So your statement is actually to show. Okay, in to show I'll put the claim. Okay, better I'll write claim. So A is equal to G raised to power I if and only if GCD of I and n is equal to 1. That is, they should be relatively prime. So my claim is first option is correct. And one more thing, if n is prime, so they said necessary and sufficient condition. So if you just say, so I'm just giving an example, let's say black, A, or maybe better color. Okay, so for example, n is prime. Let's say n is prime. Then what can you say about this G raised to power I? And just it is not written, but assume I is greater than or equal to 1, because if I is equal to 0, then this is just generated by identity. That definitely it doesn't make any sense. So I is bigger than 1. And now if n is prime, then can you say whatever I you will choose, you will get the whole the full set A, full ring A group, sorry. So if you see, if I prove this claim, then if n is prime, then whatever I you will choose, the GCD will be what? GCD will be 1, because the divisors of prime number is just 1 or itself. So that means GCD sorry, if you take I to be that prime number, then definitely this is identity. Oh, right. So if okay, uh, as I said, better and more better is to write I is strictly less than n, because if I is equal to n, then again it is identity, right? If g raised to power n is equal to identity, because a has n elements, so it cannot go beyond that. So this set is actually what? G, g square, up to and so on, g raised to power n, which has to be identity because there are n elements. That means order and everything, right? Are you with me?
Yes, ma'am.
Okay. So, so logical thing to ask is like I, if I is from 1 to n. So, just refining the question to make it more clear, that I should be, I could be equal to 1, but strictly less than n. Let's say that. If it go beyond that, for example, let's say n plus 1, then g raised to power n plus 1 is what? G raised to power n into g, and this is identity, so this is just g. So we are again repeating thing, so we are getting back g square, so it is like that. So ideal is to ask if I is from 1 to n or not. If I is from 1 to n, it is given. Okay, so if n is equal to prime, then whatever I you will choose here, which is in between this condition, then GCD is going to be 1. Is that okay? If n is prime and I is satisfying this condition. Is that okay?
Yes, yes, ma'am.
Okay, so if we prove this claim, then this part is also true, assuming this condition, and that is there. Let's assume that is there because it is better in that sense. Okay, so n must be prime. So if you say n is prime, then you can actually you will actually get whatever I you will choose other than like multiples of n, then you will definitely have this prime thing, like you will definitely have a is equal to g raised to power I. So if you are in the condition first, then definitely you are going to have your result, and this will imply n must be prime is also a case, but they asked for necessary and sufficient condition. So it is possible if n is not prime and I and n are relatively prime, then that is also okay. So this answer is possible if they have just asked that if that is the condition, then will it be true or not. But they asked for other way around question also. Okay, so let's prove this claim. Okay. Okay. So assume the contrary. So assume this is not true. Then what will happen? Then GCD of I comma n is equal to some d which is greater than 1, right? I is something, as I said, assume this condition because that is more understandable, right? So I is not like it is 0 or something. So GCD of I and n is equal to d greater than or equal to 1, right? Sorry, not equal to, greater than, strictly greater than 1. So if you say GCD is not equal to 1, that they are not relatively prime, then there must exist some GCD of I and n which is bigger than 1, right? Assume this, as I said. I'll put it in the question itself. Right, where I is from 1 to n. Okay, now let's see. So GCD of I and n is equal to d which is greater than 1. What does this mean? This implies you can write I to be m1d and n is equal to m2d. Is that okay?
yes, ma'am.
There exists some for some m1, m2, m1, m2 belongs to natural number. For some natural number, this must be true. And this implies you can actually write I to be m1. Now from this what do you get? D is equal to n by m2. So you can actually write n by m2. And since I is an integer, this will be an integer because I is an integer. This is definitely from natural number, because this is coming from these conditions, and I is itself a natural number, so this must be true. So you have, okay, oh, better to take scrolling. Right. Okay, so I is equal to this value. Now consider, then, or maybe then what will happen if you take this set g raised to power I? Then what will you get, which is actually g raised to power m1 n by m2. That is what, if you expand it out, what will you get? G m1 n by m2. I'll write it like this. This will be easy for me. This is just g raised to power I, g raised to power 2i, g raised to power 3i, up to and so on, g raised to power m2i. And this is equal to what? G raised to power, if you put I is equal to, if you put I is equal to m1 n by m2, then what will you get? This is just m1 n. And this is a multiple of n. So this is what? G raised to power n raised to power m1. And g raised to power n is identity. And so whatever power you have, it will be identity.
Ma'am,
So,
why it is up to m2i?
sorry?
Why it is up to g power m2i?
Because let's see. So what is happening here? So this is g raised to power I, g raised to power 2i, 3i, whatever you have, g raised to power. Let's say it does not stop here. Let's say it will be like it should be m2 plus 1i, exactly, right? And up to and so on, right?
Yes.
Now let's see what is this value. Okay, so this is m2 into m1n by m2. So this is equal to, this will be cancelled, and this is just m1n, and which is equal to g raised to power n m1, and that is equal to identity, right? And now let's see what is this. I'll change color better. m2i into g, right? G raised to power I. If you expand it, what is this? m2i plus I. So if you can write it g raised to power m2i into g raised to power I. And what is this value from here? You just calculated. That is identity. So what do you get here? You get here g raised to power I, which you have already in your set.
Okay.
So from this step, it will start repeating. Right, so up to this value you will get the set, and after that it is just repeating all these values. So because of this cardinality of this set, I just want to change the color. So cardinality of this set is equal to what? m2, right?
Yes.
Also I should mention here m2 and m1 and m2 belongs to n, and m1 is strictly less than I and m2 is strictly less than n, because you have said that d is strictly greater than 1. That means it is something 2, 3 or whatever you have, just bigger than 1. That means, and I is something which is equal to m1d, then m1 has to be strictly less than I, because d is not 1, d is bigger than that. So m1 must be smaller than I, and similarly m2 must be smaller than n. So these conditions are coming from the beginning. Is that okay?
Yes.
So now you have this set to be the cardinality of this set is m2, and which is strictly less than which is strictly less than n, right, from this condition. So that is your problem, because A is the set of this, you want it to be and that is equal to n. So if you want to say that, so this implies this set is strictly contained in A. It is not equal to A, because this is strictly less than n, or this has cardinality n. So g raised to power, so this is a contradiction, because we assumed a contrary. We assume that GCD is bigger than 1, and we arrive at a contradiction. This is a contradiction. So GCD of n and I should be 1, and that was the requirement. So this is one side, right? This is one side. You prove that if, or I should write, what is this side? Yeah, this implies, like, if you say A is generated by g raised to power I, then GCD has to be 1. And if you want to prove the other side is, if you have GCD to be equal to 1, then what will happen? Then it is clear actually. If you take g raised to power I, then you will get all the values. So it is coming from this proof itself, like, because d is equal to 1. So actually, if you want to write GCD of I and n is equal to 1, this implies there exists some I'm not writing m1 m2, let's say Ri plus Sn is equal to 1, and this implies you can write Ri is equal to 1 minus Sn, right? What I want to write, and so how shall I say, you want to say this set has cardinality n, right? So g raised to power I, g raised to power 2i, you are going up to g raised to power
m2i.
okay, you want, okay, let's say, yeah, actually, yeah, you can go by this itself. Why should I say r or I? So you know that m1 and m2 has to be equal to so yeah, d is equal to 1, so I is equal to m1, n is equal to m2. So from this itself you could say, so it will, yeah, it will go up to m2i, no doubt, but with different definition, because d is now equal to 1, so m2 is equal to n, so m2 is equal to n, so you have cardinality n. So this set has cardinality n, right? So g raised to power I is equal to a, and this proves the claim. So this is actually a necessary and sufficient condition. So n and I must be relatively prime. Is that okay?
Yes, ma'am.
Okay, great. Okay. Consider the map phi zx to z. So you have a map phi from zx to z, and what does this say? Which maps polynomials to its constant coefficient. So in zx, what do you have? You have some polynomial which can be written as a1 plus a0 plus a1x up to and so on, an x raised to power n. So what is this set? As you know already, it is just the collection of polynomials with coefficients in z. I is equal to 0 to n, where where ai's belongs to z for all I, and n belongs to some, oh right, I should say n first, that is important. N belongs to some natural number or 0, maybe that could be a possibility, and ai's belongs to z for all I. Okay, so this is the collection of polynomials with coefficients in z. Coefficients are integers, and these are finite polynomials, like polynomial itself mean finite. So it's just a summation of these powers. Okay, so you have fx to be this. Now, so map says you take fx of this kind. Uh, so both are same notations, x raised to power I, and it will map it to the constant coefficient. So constant is this a0. So it maps to constant coefficient. Then it has been asked whether it is surjective, whether it is injective, or okay. Firstly, I should say this is some. Let's say this is in the ring homomorphism form. Okay, consider a ring homomorphism. I am starting with this, or you can actually prove that. Okay, so okay, if you remember, what is a ring homomorphism?
Phi of a1 plus a2 is equal to phi of a1 plus phi of a2. Phi of a1 into a2 is equal to phi of a1 into phi of.
Exactly. So, do you, okay, I think I'll discuss this in the last question. But for now, let's say exactly as you said, phi of a1 plus a2, where like phi is from the ring r1 to r2. So, this is phi of a1 plus phi of a2, and also with the multiplication. Okay, exactly as you said, these are rings. So these are the maps, and so it has been asked. So this is a ring homomorphism. So I'll discuss something about ring homomorphism. It will come later, the question related to it. So for now, let's just think of this only. So this is given to be a ring homomorphism, and it can be checked using this. So what they have asked, phi is surjective or injective, or so let's see if so what do you think, is it surjective? Okay, so let's see. So for surjectiveness, what do you need to see? So phi is a map, summation I is equal to 0 to n, ai x raised to power I goes to a0. So for surjectiveness, what you need to check? It should be what? It should be for every element there exists something which maps to it. So do you have something for every element? Just think of normal things. So let's say you consider some element, what do I say, let's say a belongs to z. Okay, so your codomain is z. So a belongs to z. Then consider polynomial. Just take a. So this is itself a polynomial. A is a polynomial, right? This is a constant polynomial because n could be anything. From here you know n could be any natural number or 0. So if you just take n to be 0, then you have just a0, and that could be any number from z, right? So then consider the polynomial a, which is in zx. So this is itself a polynomial. Do you agree with it?
Yes, sir.
Then consider this. We have phi of a is equal to a, because you know constant coefficient, it will just take it to constant coefficient, and that is a for you. So so this map is surjective. Okay, what about injectivity?
No.
Why?
If two polynomials have same constant coefficient, then it will map to same.
Exactly. So if you take 1 plus x, let's say, it will map it to 1, and also if you take 1, you will get 1, exactly as you said. So this is not injective. And as you were saying, so whenever you try to give this like as you said, if you take two polynomials which has constant coefficient same, then it will map to the same thing. Just try to have the example whenever you are writing such proofs or something like counter, so give a precise counter example like this. Your statement is definitely correct, but even after saying that, better to say that, no doubt, and then give this example or any example.
Okay.
It will help you, because sometimes it happens in that statement itself there are something like, for example, you have just zero or something like that, and that statement fails to be true for such steps, then it is kind of ambiguity in that sentence. So you want to say the correct thing, but you didn't get the full marks like that. So but just try to have a perfect counter example in your thing, you know that, just write it. Okay.
Okay.
So yeah. So see, kernel of phi. So it has been asked what is kernel of phi. So in general, what is the kernel of homomorphism, ring homomorphism?
If
Yeah, phi is
domain
from.
elements maps to 0.
Exactly. So just take all the elements A belongs to R1 such that phi of A is equal to 0. 0. This is the additive identity of R2. Okay. So sometimes we write it in this form because it could be anything, like we could have modulo thing or 0 comma 0 or maybe 0 mod P. It could be anything. So you can write it in this form 0 R2. That is the additive identity of R2. Okay. So let's see that what do we have. You need to calculate this kernel. So in your case, so kernel of phi is equal to this set A belongs to, now your domain is ZX, phi of A, so better to write not A. Let's take this is fx. Okay, so any fx of this kind, ai x raised to power I is equal to 0 to n, and such that it belongs to zx, such that phi of fx is equal to 0, and a 0 of R2 is identity of z, additive identity of the integers, that is 0. So that is okay. Now from this, fx, now I'll just write fx for simplicity, and now you have phi of fx. So what is this? From the definition, it is just the constant value, that is a0, right? A0 equals to 0. So all the polynomials in zx such that their constant coefficient is 0. So how will they look like? So it is like for example a1x plus a2x square an x raised to power n. It will be like this, all type of zx of this kind, right? So what you can do, you can just pull out x from these. I'll clear it. So this is of which kind? Okay, I'll write it properly. So here you have where ai is, so now a0 is gone, so I am just writing ai is for 1 to n. So ai is belong to z for I is from 1 to n. Okay, so this is your thing, and n belongs to of course n. Now I can say n belongs to n because 0 is not there, and 0 means a0 is not here, and I can write it. And actually if you just say n belongs to n, then it is also fine. If you say like a1x raised to power, so this is your so if you want to think about n is equal to 0, then you are also there, because you just take a0 to be 0, then you have the polynomial a0, so you are not missing out something. Okay, so here what you can do, you can just write like this an x raised to power n minus 1 belongs to zx such that n belongs to n, ai belongs to z. Same thing for I is from 1 to n. And n is varying, n could be anything, you have that option. So if you see, these are all the polynomials in zx, whatever you could have here, right? Because you have constant coefficient and n is anything, so you have all the polynomials of zx. So this is actually like x into zx. This is the set like this multiplied by x, so it is like this. Is that okay?
Yes, ma'am.
Okay, so the kernel is actually generated by x. So this is correct, this is correct, so that means D is correct. So most probable option, so that is D. Okay, okay, let's see next question. Which one of the following is a UFD? So unique factorization domain, should I recall what is that?
Yes, ma'am.
Okay. So actually UFDs, PIDs, all are if domain is coming, that means actually you are saying this is an integral domain. So an integral domain, so integral domain you remember, right? That means if you take any element of the ring R, then and these are non-zero, both are non-zero, then AB cannot be 0. Okay, so the product of non-zero elements of ring R cannot be 0. So an integral domain R is said to be UFD if firstly every element for every R in R, I should say, right, for every non-unit R element R in R can be written as product of irreducible elements. 3R irreducible elements. So if you consider any element, if it itself a reducible element, then it is of definitely product of a reducible element, it comes in there. And if it is not a reducible element, then you should be able to write in the product of irreducible elements. And we started with non-unit thing because irreducible element itself has this definition that irreducible elements is being talked about non-unit elements, right? So this is the condition. And second, this should be unique. This product should be unique up to unit elements. So what I mean, I'll just let you know, or the order of product. So what do I want to say here? That means if you have, for example, R and it has been written as, let's say, R1 into R2 into R3, or maybe let's say till Rn, then this is let's say these all are irreducible elements. Then if you see, so these are there, so it should be written in a unique way of irreducible elements. And why have I said up to unit elements? Because what you can do, for example, U is a unit element, Okay, u is, for example, is unit, its inverse exists in this ring, then what you can do, you can write it like this, right? Then still it will be r1 dot r2 because u is there, but these elements are like different. So you will say because this is not equal to r1, this is not equal to r2. So these kind of things we will assume that is possible. So up to unit elements, then that means if you write it in this form, then that is also okay, and that is possible. We are just saying it should not be like you have some different element, let's say s1 s2, and these are of not of this kind, these are not related to r1 r2 in this form also. So if that is a possibility, then there is a problem. Is that okay? And order of product means if you write it r2 into r1, r3 into r2, and we are in commutative rings, so okay. So that means like if you take the different order, then it is also okay. So this is the definition. So you can uniquely write it in this form, and up to this thing. Is that okay?
Yes, ma'am.
Okay. So this is your definition. Now let's come to our question. So it has been asked which one of the following is a UFT. So you have so firstly it has been given root minus 5, right? So you have this. If you have seen the lectures, and then it has came many times.
6 is equal to 2 into 3,
Yeah,
1 plus
exactly.
root minus 5 into 1 minus root.
Exactly. Very good. Into 1 minus root minus 5. So I am not proving it, but 2, 3, 1 plus root minus 5, 1 minus root minus 5. These are all irreducible elements. And if you remember, we have proved this in the last classes, like if, how will you check if these are irreducible elements? You will just take 2 is equal to a plus, for example, you have root minus 5b, and let's say you have c plus d root minus 5. You have something of this kind. You try to write it in this form, and then it will end up that you cannot choose a, b, c and d of your choice. It could be possible that this turns out to be 2 and this turns out to be 1, and in that case this will be a unit. So irreducible element means you cannot write it in the non-unit product of two non-unit elements. So that is your thing, right? So 2 is not 2 is equal to this value. If you can write it in this form, then with the, and no one will be the unit, then then this is a reducible element, otherwise irreducible. So you check it, okay, and no one should turns out to be a unit if you want to write it, if you want to say that this is reducible. Okay, yeah, but it will end up with the contradiction if you say that these are both non-units. Okay, so you can prove for all four, and also 2 is not equal to some unit 1 plus root minus 5. Okay, like also you, as I said, it should not be of this kind also. So it should not be like you have some unit and you multiply it with that. So if you want to really check all these things, you should know what are the units in this set. So units are, how will you check units, how will you calculate units? That means if you are saying a plus b root minus 5 is a unit if a plus b root minus 5, and these are integers, okay, because you are in z root minus 5, so we can write all the elements of this kind, right? So you have some, if this is equal to 1, if there exists some c plus d root minus 5 in z root minus 5, such that now you check it like ac, what will you get? minus okay, so when you multiply this and this, you will get minus root, yeah, minus 5, and this will be BD. And if you take minus root 5, am I doing right? So you have AD plus PC. Now you want to say, so that means this is equal to 1 and AD plus PC is equal to 0. Now you just check it, like what all things you are getting. So whatever ABCD you will get, this will give you units. Okay, what are so whatever, if you can find out ABCD, then for that AB you have this, then it will be a unit. So I guess what will turn out, like 1 and 1 or minus 1 will be a unit, nothing else. So you can check that. Okay, right. So if you want to really check all these things, then you should check from the definition all these things, like these are irreducibles, like what are all the units, and then you can actually relate these R1 and R1 type things, right? So that need to be checked. Is that okay?
Yes.
Okay. Right. Let fx is equal to, so it has been given. Okay, so you have this polynomial fx, x square plus bx plus c, and this is a polynomial in zx. So you have integer, so these are integer polynomial, like coefficients are integers. Which of the, and this is a quadratic polynomial. Okay, so if fx can be also this, yeah, and so why I said this is, and this is not a monic polynomial. Monic means monic, this is a monic, this is not a linear monic. Okay, monic polynomial means this implies highest degree term, degree of fx, I'll write how shall I write, degree of fx is equal to 1, no, degree of fx is equal to n, and an is equal to 1. So what does that mean? The highest degree coefficient, the polynomial with the highest degree power, its coefficient is equal to 1. Okay, so that means if I write fx to be a0 plus a1x plus up to and so on an x raised to power n, then the highest degree term, it should be equal to 1. So if degree is equal to n, because you can actually write an plus 1 and those could be 0. So what we are saying, the highest degree term, so whatever degree it has, that means its coefficient is non-zero, and that coefficient is equal to 1. Okay, so that means monic. So I want to say that as this is monic, this cannot be a linear polynomial. Linear means because this coefficient is there to be 1, it is not possible that the coefficient of x square is equal to 0, then only you can say this is a linear polynomial. So this is actually a quadratic polynomial. So what has been asked, if fx can be factored into linear terms in zx, then it can be factored into linear terms in qx. So do you feel that this is okay? So you have fx, which is equal to x square plus bx plus c, and now they are saying that it can be factored in linear polynomials. Okay, then okay, so factored in linear terms in zx. So in zx means m and n belongs to z. Is that okay? So from the line, what does that mean? Fx can be factored into linear terms in zx. That means when you factor it out, you get these places to be integers. So whenever it has been said that it is factored in this ring, that means those factors are itself in this ring. So it is not possible that it is something like this. Okay, this is not the thing. So if they are saying it is factored into linear terms in zx, then that means both of these elements belongs to zx. That means m and n belongs to zx. And why I have taken this to be for example 1, this is 1 because this is a monic polynomial, so you will get this only. Okay, now, so this is the case, right? Now what they have asked, if fx can be factored into linear terms in zx, then it can be factored into linear terms in qx. So what does that mean? If you consider fx, so since this is in zx, what does that mean? This is also in qx. Is that okay?
Yes, ma'am.
So these are the set of polynomials with coefficients to be rational numbers. And as you know, integers are also rational numbers. So you have all the polynomial inside this. Now you are saying fx can be written as factor into in zx. So these both things belongs to zx. So again, this will be in qx also. So in qx itself, it will be factorized, right? So
Yes,
you
ma'am.
so this statement is true, right? And now if you second part, if fx can be factored into linear terms in zx, then it cannot be factored into linear terms in qx. Then definitely this is not a thing. So if you want to write as an example, as I said, better to give examples. So you just take 4x plus 4. As you know, this is what, x plus 2 into x plus 2. So this is factored in zx. These both things belongs to zx, right? So this so x square plus 4x plus 4 is equal to x plus 2. X plus 2 is also factored in qx. Okay, this is also factored in qx. So they said if fx can be factored into linear terms in zx, then it cannot be factored. So that is not the case. It is also factored in qx. Okay, because whenever you have subset thing, now if I change zx to be something else, let's say you have some r and let's say you have some ring s, okay, and you know r is contained in s, then this statement is always true. Like first statement, if fx can be factored into linear whatever, if you just say any factors, okay, factor, if it can be factored in r, then it will be factored in s also, whatever way they are asking. Okay, now fx has at most two roots over z. So okay, about two roots, so you have quadratic equation. As you know, actually you will have two things, but two factors. Actually this comes from the fundamental theorem of algebra. Do you know that?
yes.
So do you remember the statement?
Nth polynomial has at most n roots.
Okay, yeah, so right, so in, okay, I should say, actually this is the statement in complex number. So if you take any polynomial in complex number integers, like coefficients are coming from complex number, then and degree of fx is equal to n, where n is something where n belongs to maybe natural number or 0. Let's say natural number. Then fx has and at most n roots. Oh, actually n roots in C. N roots in C. So as I said, fx is right. Okay, as you said, we are not repeating roots or something, so let's say at most. Or you could say, because repetition is also possible, for example, -2 is coming for both root, -2 is the root, so at most n roots. But actually, it's the real statement is if so in this statement itself, it just say then fx has a root. So this is actually a statement first, and then because of induction, you use induction, you take, for example, you have some n degree polynomial, and as you are saying this it has some root, then you can actually write it something complex number here, let's say complex number c, and you can again write it like this, and the degree of this will be n minus 1 or less, right? Degree of this will be n minus 1. So because of induction, you will get n roots, at most n roots. So this is so this is itself okay, like if we just say fx is a root. But as you said, we can actually have this, sorry, is at most n roots. And now if you see, if you just go into zx, fx belongs to zx, then still it will be a polynomial in complex numbers. So again, it has to have at most n roots. So n means 2 roots, because fx is given to be x square plus ax plus b. So whatever degree you have, you will just take like at most that roots. Okay, so yeah, exactly, this statement is true. No, because so most probable answer is A and C. Okay, let's move to next question. Which of the following statements is true? Okay, every UFD is a PID. So principal ideal domain is like PID. You can write it the short form. So you remember the definition. So UFD we just discussed. Principal domain means PID is I'll change the color. PID is what? An integral domain. So these are all definition for integral domain. Integral domain are such that R is equal to generated by some element A for some element A in R. So there exists some element, one second, whatever I wrote, actually for some non-unit. Oh no, wait a minute. So integral domain R. So why am I confused? If you remember this statement, you can help me. So this is what AR, where R belongs to R, right? So for some non-unit should be a non-unit. So why am I concerned about this? Because R is always generated by 1, right? If you take, because what is this set? 1 into R, where R belongs to R. So you have all the elements, no doubt, right? Are you with me?
Yes.
So this is not about any unit element. So if you have any unit element, then its inverse exists. So because of that, what will happen? You have that unit element U, and if you say it is generated by that unit element, then you have U into U inverse in your set, and whatever all the elements also. So because of this, you will have 1, and now 1 into r will be there, because this is an ideal kind of. Oh, sorry, exactly. So I missed that, but yeah. So because obviously this is not the thing, so this could not be a definition. Yeah, sorry, I lost my connection. Yeah, so integral domain are such that for any ideal, I, so yeah, I forgot the definition. Any ideal I is equal to generated by some element a, for some a belongs to r. So if you take any ideal, then it is generated by some element a. As I said, r is always generated by any unit element, let's say 1. So this doesn't make any sense. And if you say also, which I was writing incorrectly, so if you say this is generated by some non-unit element, will that be possible? Do you think that if this is a non-unit element, can I say that r is equal to this where u is a non-unit element? Can it be possible? This is not possible. Why? Because if you are saying r is equal to generated by some non-unit element, as you know 1 belongs to r, that means some u into r is equal to 1, right?
Yes.
So that means it has inverse, right? So you cannot be non-unit. So yeah, that definition doesn't make any sense, right? Okay, so yeah, so this is not something which I should discuss. So this is integral domain R such that for any ideal I is equal to a, generated by a for some a belongs to R. Okay, so this is the definition of PID. So it has been asked, every UFD is a PID. So let's see if that is true. So one statement is for sure true, but okay. So I'll write it. There is a theorem which I'm not proving it, but it is a very, so you can remember these things and you can try the proof and see the books or Google it. So every, that is involving proof, it is not direct. Every PID, so PID is for principal ideal domain, is a UFD. So this is statement, I'm not proving it. So every PID is a UFD and it is involving, proof is bit involving, right? So every PID is a UFD, so that means the second statement definitely true, right? So let's see if the other statements are true or not. So this is true. Now for second one, for first one, let's say this A, every UFD is a PID. Do you remember any example? As you know, one statement is true, but it could be possible that all of the above is the answer. But let's see, every UFD is a PID. Do you think that, or do you have any example to tackle this? Okay, let me do that. So I'm giving, so let's consider ZX, which we were discussing earlier. So there is also a theorem about it. So there's a theorem, if R is a UFD, then Rx is also a UFD. You can try that. So this is also a theorem. Now because of this, since you know that since Z is a UFD, is that true? Z is a UFD? Because you take any element n belongs to Z, then you can write it in only one form, because primes are itself coming from, you can actually write it as the product of primes, and that is already a well-known theorem that you can write it as the product of primes up to, again, like you uniquely, you can write it uniquely up to order, like you can write it p2 into p1 up to so on pn, whatever. So this is, so because you can write it in this form, so this is a UFD. Now so this implies ZX is a UFD, right, because of this theorem. So these are standard theorems, and I'm proving it. ZX is a UFD. Now what will happen? Sorry, yeah. Now this is actually not a PID. Why? If you remember, I've given an example earlier. If you take in ZX this ideal 2 comma x, then this is not generated by the ideal. Let's say the ideal I is equal to 2 comma x is not generated by single element. Okay, so have you tried this proof, as I asked earlier?
I didn't get.
Sorry?
I didn't get. I tried, but
Okay. So actually, okay, I can try. Okay, it's already sent for, but okay. So I is equal to 2 comma x. So if you take this, just think of what will happen if you say that this is generated by some element A. So because you want to say that this is generated by single element, so what should happen with A should be a multiple, sorry, yeah. So as you know, generator of this 2, like, is contained in A. That means, so this is what this is the set, what, so, how shall I say? Yeah. So this is what, this is all the elements 2 into fx, where fx belongs to zx, right? So this is the set by multiplying 2, right? So this is contained in this. That means it cannot be a multiple of some x or something, otherwise 2 will not be there. So this should be 2 should divide A, right? So it should be a multiple of 2 or something, like 2 should belong to A, right? That means this should divide 2 something, sorry, other way around, sorry, other way around, because if you think of 4, that is bad now. So what should happen? A should divide 2, right, because it should be a multiple of in that set. That means 2 is equal to A into fx, right? Now if you take any polynomial fx, you are in zx. So if you take 2 is equal to A into fx, this will imply that A itself should be divisible, should divide 2. That means what are the options for 2? So that means A should be what? A should be either 1 or 2. Now it cannot be 1, because that will be the full matrix, because as you know, in this set 1 is not there. 1 does not belong to 2 comma x, right? Is that okay? This is not the whole ring, that is for sure, because either these are the multiple of x, or these are the multiple of 2. If you combine these things also, but one will never come here. So 1 is not there, that means this is not the whole ring, because 1 is always there in zx. That is multiplicative identity. Now you have, so as you said, this is generated by A. So what you got at the end, you get A should be either 1 or 2, because of this thing. Now it cannot be 1, as you already know. Now the only option is 2. So if you say this is A, if you say A is equal to 2, if A is equal to 2, then this set, this 2, then x does not belong to generated by 2, right? Because these are all what? The multiples of 2. These have all the elements which are multiples of 2. So x will never come, because it is not a multiple of 2. You cannot write it as something 2 into fx, right? Is that okay?
Yes.
So because of this, now no option is available for you. So you cannot find some a. So a cannot be equal to 2 and a cannot be equal to 1. So there is no possibility. So this is not a principal ideal. So Zx is not a principal ideal domain. Okay. So this is the proof for this is not a principal ideal. Now, so this is wrong. Every UFD is a principal ideal domain. That is wrong. Now every integral domain is a PID. So that is also not true, because you take the same example. Zx is what? Zx is, sorry, yeah. Zx is integral domain, no doubt, because Z is an integral domain. Now if you take any two polynomials, then product is 0. This implies that fx and gx has to be 0, or actually these are UFDs, so definitely it has to be integral domain. Okay, so this is an integral domain, and now again consider 2x, then you have this example. So C is not correct. So only option which is correct is every PID is a UFD. Okay, I hope this is clear. Well, let's go to the last question. Okay, let R is equal to A comma B such that A and B belongs to Z. Okay, so this is a ring with component wise addition and multiplication. So what you are doing, you are just addition is basically a1 b1 plus a2 comma b2 is equal to a1 plus a2 comma b1 plus b2. Okay, and if you take multiplication, that is again component wise. You can check this is a ring with all these with these operations. Okay, so this is a ring. Now consider the map. This is a ring homomorphism. So which of the following is a ring homomorphism? So this has been asked. Now first you have, okay, so as I said, I'll say about something, ring homomorphism here. So as we know, so ring homomorphism, the definitions was clear. If I just take R1 to R2, then this is a ring homomorphism if first phi of R, not R, sorry, just take A and B. Phi of A plus B should be phi of A plus phi of B for all AB belongs to R, and second phi of A into B should be equal to phi of A into phi of B for all here R1, because domain is R1. Okay, so this is your ring homomorphism where R1 and R2 are rings, no doubt, because we started with rings. Now, so some properties you can actually see. If you take phi of 0 plus 0, then what will happen? Yeah, tell me.
0.
Yeah, so this is 0. Have you tried the proof?
Yes.
Okay, great. So I'll just complete it. So as you know already, what can you do? You can just subtract by 50. Okay, because the inverse exists in addition, right? Because in a ring, it is a Abelian group with respect to addition. So you will get this, and this is just 0 of R2, like additive identity of R2, and this you get phi of 0, and here 0 is R1, the additive identity of R1. Okay, now so you have this condition. So this is the second thing, now let's think about what do we have about multiplicative identity. So if you have seen that, so I'm starting with this. So I'll come to this question. So here you will have phi of 1 is equal to phi of 1 into phi of 1, right? From the second property, we are not doing anything, just not this is the uh, multiplicative identity of R1. Phi of 1 R1 minus right now you have phi of 1 R2. So what we did, we took it in the same side. Okay, we took it in the same side and we just take it took the common phi of 1 R1. So here you can actually write it 1 into R2, because 1 into R2 is the multiplicative identity of R2 is from the definition, it's a multiplicative identity. So this you can write it, and you can, because of this, just take it from this side and you take this common. So from this, what now if now what should be the integral domain? So these elements are belongs to what in R2, right? Because these are the images, so these are R2 elements. So what should happen if R2 is an integral domain? So I'm going to our question now. So if you see in our question, R2 is your Z, right? R2 is Z. So that means this is an integral domain. You know that this is an integral domain. So R2 is an integral domain, then what does that mean? Either this is equal to 0 or phi of 1 R1 is equal to 1 R2. Either this is 0 or this is 0. This means this is equal to 1 R2, right? Now this or this, right? So you have two options to have your thing. So either multiplicative identity of R1 should map to additive identity of R2, or multiplicative identity of R1 should map to multiplicative identity of R2. Both is fine. Okay, for now, at least with this information. Okay, so let's come to our question. So you have these three things. Let's see if any of these properties are not going on with your thing or not. Okay, so you have a comma b goes to a plus b. So that do you think this is a ring homomorphism? Firstly check what is the so first check where additive identity goes. If you take 0 comma 0, it will go to 0, and that is the additive identity of Z. That is okay. Now if you take multiplicative identity, here multiplicative identity is 1 comma 1, because these are component wise addition and multiplication. So here it will stays the same. It will behave as identity if the element is 1 comma 1. So this will be just a1 comma b1. So multiplicative identity is 1 comma 1. Now where this is mapping, this is mapping to 2. But in your thing, if this is an integral domain, then either it should map to 0 or it should map to 1. It cannot map to any other thing. Okay, so this is a problem, right? Now is that okay?
Yes, ma'am.
Okay. Now if a comma b goes to 0, can you tell me about if this is okay or not? Okay, let's see here. If you see, both of these properties are okay, because 0 goes to 0 and you have both these options. So this is okay, right? So both of the options can be possible, and that is okay. So identity, so here identity 1 comma 1 also goes to 0, and that is okay from the thing you have. Now if you want to check this is a ring homomorphism, you will check these two properties, right? So I'll change color. So these two properties you will check. So phi of 0, phi of any a plus b is equal to 0, and the right hand side will be phi of A plus phi of B, and any element is going to 0, that means 0 plus 0, this is 0. So these two things are equal. Similarly, if you take any two elements, this value will be 0, and this value will be 0, this value will be 0. So these are also okay. So both of the statements are agreeing. So this is a ring homomorphism. So this is a ring homomorphism, right? And what about this third one? So if A comma B goes to 1, is that a ring homomorphism?
No, ma'am, it is dissatisfying the first option.
Yeah, exactly. So 0 comma 0 is not going to 0. That is a problem. Exactly. So this is so the second one only is the ring homomorphism. So yeah, I'm done with my questions. Now you can ask your questions.